All right, section 2.4, we were taking a look at applications of trig functions, and what we had specifically looked at last time was something called solving a triangle. And to solve a triangle simply means finding all the sides and angles. They have to give you 3 of them to start with. So it either needs to be all 3 sides, which is an option, and we had that given to us. Actually, I take it back. We don't have that as an option yet. That's later on. They have to give you either 2 sides and an angle or 2 angles and a side. So this was our first one, example number 1. We were given 2 angles, correct? Yeah, we were given 2 angles and a side. One of the angles that they're giving us, though it doesn't actually get written in, is this right angle right here, which it told us that we had a right angle up in the original directions, right? So one of the angles they gave us is the right angle, and then we had a second angle and we had a side. On this one, which was what I was referencing before, we have an angle given, it's the right angle, but then we're given 2 sides instead. So either 2 angles and 1 side or vice versa. And I talked about, as we left class last time, the fact that, to be honest, the real applications are easier in this section than solving the triangle because we're not asked to find all 3 pieces of information. We're only asked to find typically 1 of those 3, which means we don't have to do nearly as many steps. So I'm going to take a look at our first real example, real life type of example. And we're taking a look at something where the sun is creating a shadow. So it says, suppose the angle of elevation of the sun is 23.4 degrees. Find the length of the shadow cast by Diane Carr, who is 5 feet 9 inches tall. So we've got someone, and I don't draw well, so here's our Diane Carr. You can humor me a little bit. There she goes, okay? And there's a sun, and the sun is over here somewhere. Just for the way that I've drawn my picture, I'll put my sun over here. And the sun is casting a shadow from where it is to where Diane is. So this shadow looks something like this. Well, at least the sun is shining down something like this, and the shadow that's cast is down here on the ground. And what we should be seeing then, that's not very straight, is it? Let's try it again. It's a little bit better. What we should be seeing drawn when we sketch the picture that it's describing is a triangle. Do you see a triangle? Okay, good deal. So we have to be able to see the triangle that's being described in order to proceed through the problem. And the triangle, and I'll draw it in a little bit more strongly. Let's change color. Let's go to, I don't know, how about orange? We haven't done orange yet today, and we'll make it a little thicker. So the triangle is actually right in here. Okay, roughly speaking. And it's a right triangle because we're assuming that Diane Carr is not leaning, right? She's not leaning. That would be weird. She's just standing up, normal, standing straight. So here's my right triangle, or my right angle for my triangle. It gives us a little bit of information. It tells us that the angle of elevation is a certain degrees, and it tells us how tall Diane Carr is. And just like on the last 2 problems, that's exactly what we need. We need 2 pieces of information plus the fact that there's a right angle. So the 23.4 degrees in angle of elevation is always from the horizontal up. So the angle of elevation is right here. So this one is the 23. Hang on, that didn't work. 23.4, there we go, degrees. And then Diane herself, this height is 5 feet 9 inches. Now, we talk in terms of heights like that, right? You could probably all tell me how tall you are in feet and inches. That's kind of our normal way of describing that. But that's not really very conducive for doing mathematics with because there's 2 units there, right? So if she's 5 feet 9 inches, we've got her height both in feet and inches represented, and we really would rather have it represented in one or the other. And it doesn't even really matter which one. So what would you guys like to do? Put her height in feet or put her height in inches? Somebody pick one for me. Inches. Chloe says inches. So if we're going to do her height in inches, then the 9 inches is already there. How do I get the 5 feet into inches?
5 times 12.
Yeah, 5 times 12, because there's 12 inches in a foot. So if I have 5 times 12 and I add my 9, what will I get? Yeah, it's 69, right?
Oh, sorry.
Is that right? Is it 69? I'm doing that in my head real quick. Yes, Reese is nodding, so that's good. Okay, 69 inches tall. Okay, everybody good? If you change it into feet, it's fine too. The problem still at the very end, we may want to put it back in feet when we're done. It doesn't actually tell us how to put the answer, so we have some flexibility. My math lab might tell you how long is the shadow in terms of feet or inches, in which case that tells you kind of which one to put it in. But we're going to do it in inches since that's the one that was mentioned, so we'll do it in inches. All right, so we've got a 69-inch tall person, and we've got this angle of elevation that's 23.4 degrees, and this right here is the side that we want to find. We want to find how long the shadow is. Okay, so what trig function relates the 69-inch tall person, this 23.4 degrees angle of elevation, and the shadow's length? Sine, cosine, tangent. Which one? Okay, so sine is, I didn't mean to type that, opposite over hypotenuse. Do we know anything about the hypotenuse? We don't. And cosine also has hypotenuse in it. We don't know anything about the hypotenuse. Tangent's the one that we want here because tangent is opposite and adjacent. And we do have the opposite angle, opposite from the angle, which is her height, and the adjacent to the angle, which is the shadow is what we're looking for. So we're going to use tangent on this one. So this is tangent of the angle measure we were talking about, or given, 23.4 degrees. And then the opposite is her height, that we said is 69 inches. Over the unknown, we'll just call it x for the length of the shadow. So what would I need to do to solve for this quantity? Okay, so we don't want to multiply by 69, but you're right, we want to move the 69 and the x away from each other. We'll multiply by the x. And I know that sort of feels like, well, aren't you just moving the x over to like the other piece that it doesn't want to be attached to? And we kind of are, but we've got to get the x out of the denominator. So we do need to move the x. So at this point, if I think about writing what I have out, it looks like this. What would be the next step that I would need to do then to solve for x? Yeah, we would divide by the tangent, not just the 23, but the tangent of 23.4 degrees. All right, so if you grab a calculator, make sure you're in degrees. I don't have mine today. I think it got left at home accidentally. My kids were doing SOHCAHTOA last night in geometry. Randomness, but that's the way it worked out. So somebody tell me, what do we get when we do 69 divided by tangent of 23.4 degrees? And I don't have this written down either in inches. I've only got it written in feet, so I actually don't have the answer at all. What'd you get? Okay. And it didn't give us any length to put it to. 45 will be just fine, and this would be inches. If I had done this, and then I looked back at the directions and I was like, oh shoot, it said to do this in terms of feet. And I just did it in terms of inches, and I don't want to redo the whole problem. What would I be able to do at this point to turn this into feet? Divide by 12. And if we divide this by 12, just so that you have it written in there as a reminder to yourself as well, what will you get in terms of feet for this one? We'll go with 2 decimals as well. 13.29 feet. So there's a couple of different versions of an answer there for us in terms of inches and in terms of feet. I don't think of any place where you would need to turn it into feet and inches like her height was to begin with. We don't typically see that done. That's not a natural kind of a question that would be. It would be either in inches or in feet. Okay, any questions on that one? Let's try another one. So we're talking about some buildings. So the angle of inclination, okay, so incline meaning the same thing as elevation, right? So the angle of inclination from the base of the John Hancock Center to the top of the main structure of the Sears Tower is approximately 10.3 degrees. If the main structure of the Sears Tower is 1,451 feet tall, how far apart are the two skyscrapers? Assuming the bases of the two buildings are at the same elevation. Let me just make one comment here at the end about why this is thrown in here. Probably, given that you're in Oklahoma, you probably wouldn't even think that this would be necessary. You would assume that this was the case. But there are places within our country where buildings are not at the same elevation. That's atypical. We visited Seattle this summer. Seattle is built into massive hills. There's they're kind of underground kind of spaces and things like this. The beginnings and the endings, if you will, of the buildings, and so forth. They don't start at the same elevations. So that's why this is thrown in here at the end, is number one, because it really does need to be said. But number two, because depending on your previous exposure to what buildings would look like, you might have a different idea. Does that make sense? So they're making sure to establish that there is the same base level here for our buildings. So we're going to draw our two buildings. So we have one building and we have another building, and it really doesn't even matter which one's taller than the other one. I drew them as different, but it doesn't really matter. One of them is the John Hancock building, so I'll just abbreviate it like this. And then the other one is Sears. And it says that the angle of inclination from the base of John Hancock to the, hang on, get that back on there, to the top of the Sears Tower, definitely not drawn to scale, is 10.3. So this is the angle of incline between the base here and the top here. I believe that's how it described it. Does that sound right? Pictures seem to match. There's one more piece of information it gives us. What is it? The height of which one? Sears Tower. The height of the Sears Tower is 1,451 feet. So this height right here, all the way to the bottom, though I didn't mark it that way, is 1,451 feet tall. And it's wanting us to find this piece at the bottom, right? It wants to know how far the buildings are apart. So what is the trig relationship between the known quantities? It's tangent again, okay? So tangent is opposite over adjacent. We still don't know anything about the hypotenuse here, so we're not using sine or cosine. So our tangent now is the tangent of 10.3 degrees equals what? 1451 over x. And what's the process to solve for x? Multiply by x, and then what? Divide by the tangent of 10.3 degrees. All right, so if I take 1451 and I divide by tangent of 10.3 degrees, what do we get for the length of x? It's long, comparatively anyway. I have 3.4. Is it 3.3? It's 3.4 if we round the next one. Okay, no problem. Always a possibility of a typo on my paper too. So we have almost 8,000 feet apart. So picture was not drawn to scale, but you kind of knew that to begin with, right? I mean, this is definitely not a 10-degree angle I've drawn in here. So the pictures don't have to really have a lot of accuracy to them. They're really just trying to give you some perspective of where the sides are in relation to the angles you're given, okay? All right, another application that we're going to take a look at in this section is called bearings. So bearings are a topic that occur in navigation and surveying. They're used to specify the location of one point relative to another. Now, you use ordered pairs, sort of in an XY plane, to do the same thing. It's always in reference to where one point is in reference to the origin, right? We're always going back to the origin. What this is doing, though, is it's referencing how far apart or the angle measures and so forth between two different points. Typically speaking, this is used in navigation, like in the ocean. Like that's where you see it used most, but certainly isn't the only way that it can be done. So if we have 2 points given like this, and we'll call them P and O. If I want to know how I get from O to P, right, we're just going to go from O to P, there's going to be two directions that are being used here. We use the direction of how far north or south it goes, and we always reference that one first. So in this case, we would be going north, right? And then we go from the north, we go over this way to the east or west. Which choice is that one? Do you know? How good are you at directions? Chloe's right. It's west. So this is west. So north, south, west, east. Goes like this, if you remember from your directions, okay? So the way that we would describe this picture, and I'm going to put an angle measure in here so that we can actually give a value to this. So if this is an image that we were being given, right, something like this, what we would say is something like from O to P, we go north first, and then we go 40 degrees west. Notice it doesn't tell us how far along that direction, but it's giving us the general direction that we're going. That's what bearings do, the direction that we need to go. All right, so let's actually do a different one. Let's say the picture looked like this to start with. We're still going to say that we're going from O to P. So how would you describe this in terms of bearings from O to P? What would we describe first? South, okay? South, and then what? 21 degrees, and then it would be east. So we would go south and then 21 degrees east. And if we were on a boat, right, you'd set your dials and so forth to give you that bearing, and that's how you would know where to go from where you are. So we're going to actually start with some information pieces given, this time going the other direction, and draw what these pictures would look like. So we're going to draw the bearing that's described below. So I'd like for you to take just a second to do this. They don't take very long to draw. So draw in what south 50 degrees west is and what north 13 degrees east is. And then we're going to make sure that we have the basic idea of that drawn in. And I have protractors, but I don't have them here today. I'll bring them on Monday when we come so that we can actually draw these with a little bit of level of accuracy. We're just going to eyeball it for today. But when we do it on Monday, I'll have the protractors here so that you can have experience to practice with those. All right, so your picture for south 50 degrees west, you should have gone down from some point. You just need a point to start with, so that was my point. You went down south, and then if you go west, you would go something like this, and you should have marked in 50 degrees. Does yours look like that? Approximately. We'll get the 50-degree business with the protractors next time, but other than that, it's okay. Lovely. And then we have north 13 degrees east. So here's my point I'm going to start with. So north would be straight north. East is to the right. It's not very far, so it looks something like that. And when we would be marking that we are at 13 degrees right here. Okay, is that good? Okay, so bearings is one application that we're looking at in this section. And then there's a third application. This is our last one. Our third application in this section is called simple harmonic motion. So we're going to write in this very long description first, and then we'll talk about a picture or an image anyway of where you have seen maybe this used before. So an object that moves on a coordinate axis is in simple harmonic motion if its distance from the origin D at time t is given by either D equals a cosine, that W is actually the Greek letter omega, so it's a cosine omega t, or D equals a sine omega t. The motion has amplitude A. That makes sense from what we've done. We've got something called maximum displacement. The maximum displacement is what the amplitude is from its rest period. The period of the motion is 2 pi over omega, where omega is positive. The period gives the time it takes for the motion to go through one complete cycle. Okay, so some images of simple harmonic motion. We're going to do some examples, but a real basic image that I imagine you've seen before is a swing, like children swing on. Okay, so simple harmonic motion would actually mean like you took the swing to the very height. You know, you're standing behind the child. You've pulled their swing up high, and you let them go, right? And what happens is the swing comes down, and it goes like this, and then it comes all the way back to where we were before, and that's simple harmonic motion. Now, the caveat to that is with the example of the swing, we have the effect of gravity that eventually slows the swing down. But if you can imagine what it would look like if we didn't have gravity and the swing kept going back and forth forever, never slowing down, that's actually what simple harmonic motion is. Does that make sense? So we've got an effect of gravity that doesn't quite play in very nicely here. But other than that, it's a pretty good image, kind of an example. You may have seen people use them on their desks for some reason. They're the silver balls. There's usually like 4 or 5 of them or whatever. You pull one of them and you drop it. Huh?
It's called a Newton's cradle.
Newton's cradle. Thank you very much. And then it falls back this way and it comes right here. Like, same idea. That's your simple harmonic motion. The examples that they're going to give us here are going to be about springs. So if you imagine a spring being pulled down, like it's really tight spring, and then you let it go and the spring comes up and then it comes back down. Again, we have the tightening effect that eventually slows that whole process down. But the initial one is really pretty good at mimicking this simple harmonic motion. So maximum displacement. Displacement is just how far away that you are from rest. So if you imagine the swing, the maximum displacement is how far the swing's been pulled back out to the back or how far it's swung forward to the front, right? The maximum displacement, that's the A, the amplitude. And then the period is exactly what we'd expect the period to be. The period is how long it takes to get back to wherever it was you started. Okay, that's what it has been when we've looked at these kind of images already. So let's do an example. So an object is attached to a coiled spring. We're going to write an equation for the distance of the object from its rest position after t seconds. So the object is pulled down 6 inches from rest and then released with an amplitude of 6 inches and a period of 4 seconds. Okay, so this is the description. So we're going to write some of this out in terms of the letters, if you will, the variables that it's described back over here with the omegas and the d's and the a's and those kinds of things. So to start with, our d is actually a negative value. And the reason it's negative is because it says it's pulled down. Okay, so it's starting up with a downward pull. And it's pulled downward 6. So the D is -6. And that's when it's furthest from its resting position. So that D is actually the same as what our A is being called. Our A, our amplitude, is how far away we are. So A is -6. Also, we have to decide, because we didn't actually talk about which one we would use, which of these two equations it is. Is it sine or is it cosine? Well, if you imagine our sine and our cosine graph, they're really the same thing, just shifted, right? I mean, so technically you've kind of got either as an option, but there's usually one that's a little bit more natural based on the description that you're given. This description actually starts as it's already been pulled down. Cosine is the one that does that, right? Sine starts at a rest place. Cosine starts at a maximum or minimum. Now, typically it starts at a maximum, right? It usually starts up here at 1. How do I get it to start at negative? Well, you make the amplitude negative in front, right? So you start with a negative value. So we have D equals a cosine omega t because it's furthest from rest, right? It's further away from, it's not at rest in particular. And the A is -6. So far we have our A value. We can fill that in. So D equals -6. That's not a good equal sign. Let's try again. -6 cosine omega t. Okay, the negative 6 is kind of a nice, clean one to find. Omega is a little trickier because they don't tell us what omega is. They almost kind of tell us what the amplitude is, right? I mean, the description is pretty clear. But they do tell us a way to find, if you're thinking about it the way that they're describing it, the way to find omega. They tell us what the period is. What is the period?
4 seconds.
It's 4 seconds. Now, what is the period normally when we're working with a cosine graph? It's normally 2 pi. So our period is typically 2 pi, right? This is what we're normally comparing it to. So what do we need to do? Well, we need to take that normal period. We will divide it by omega, and it will equal 4. That's going to be our period. You've found period, but you've never had to go backwards and figure out what the value is in front. So this is kind of a going backwards step. So instead of actually being given omega, we're being given the period and we're going backwards. We should be able to find omega doing this, right? So just like we were finding our tangent values on the previous examples, we multiply by the omega. We have 2 pi equals 4 omega, and then we would divide, where'd my W go? Omega is on the wrong, oh, that's what I did. Those cancel, there we go. And then I would divide by the 4. So my omega is what, if simplified? Thank you, pi over 2. So omega is pi over 2. So the completed version for this formula would be negative 6 cosine pi over 2 t. So that's the equation at once for number 7. So A can be negative, certainly. We've had negative, right, when you've graphed them for me before, too. It just reflects the graph, okay? And this one does have a negative because it's actually starting at its lowest value because it's being pulled down, and then it's going to bounce back up.
Because I don't know, did that say absolute value?
That's because of the way it's describing what it is. So amplitude itself is a positive value, but displacement, or the A value at the beginning, still be negative. So the amplitude is still 6, because it just measures how far away you are from rest, but its value is a negative number. Right? So if I asked you, what's the amplitude of this? You would not say the amplitude is negative 6. You'd actually just say the amplitude 6. Okay? But the value for A is still negative 6. Okay, we have another one. Same directions. We're finding the equation that it's giving us. This one says an object is propelled downward from its rest position at time 0 with an amplitude of 5 inches and a period of 2.5 seconds. So let's first start with what D is. D, the displacement. What is the displacement away from rest? It's negative 5. Does it start at rest or does it start at its maximum displacement like the last one? This one starts at rest. So because it's starting at rest, we're not going to use cosine. Cosine starts at its maximum displacement, either at its height, positive, or like on the last one was the negative. So since it's starting at rest, this one's telling you that you're going to be working with a sine graph. And I'll write it out actually fully. So it's the D equals A sine omega t. That's going to be our equation because sine starts at rest. All right, we need to find our A value. So A is what? It's negative 5. And the reason it's negative is because it's going to go down first. Sine typically goes up first, right? So I need it to go down first, so I do have A as a negative 5. Amplitude's 5, but the A value is negative 5. And then how do I find my period? Well, what is the period normally for a cosine graph, or sine graph, excuse me? It's normally 2 pi. So I want my period to be 2 pi divided by the omega that's there, and it tells me that the period is what? 2.5 seconds, yeah. So we're going to solve this. Multiply by omega. So I have 2 pi equals 2.5 omega, and then I'll divide by the 2.5. This one feels a little bit awkward because I have a decimal and a fraction to clean up in here. I do need it to not have that decimal inside of that fraction. That's not good. Any idea how I could clean up the fact that there's that decimal there? There's more than one answer to this question. What could I do to make that 2.5 a whole number instead of it being a decimal number? We can multiply it by something. What's your idea? Well, we need to multiply. We don't want to just multiply by 2.5, because if I multiply by 2.5, what's 2.5 times 2.5? No. What happens when you multiply 2.5 times 2.5? Can somebody do it for me, please? Like half the class is sitting with a calculator there, and everybody's just looking at me. Y'all can do it. We get 6.25. Did we get a whole number? No, in fact, we got a longer decimal. I need to multiply by something to get rid of the decimal. 10 would be a perfect number. 10 moves decimals. So if you don't know what else to do, 10's a good choice. 10 will move this decimal and make it a 25. It's not the only choice, by the way, but it is one that works. So if I multiply this by 10, I'm going to get 20 pi on top, and I'm going to get 25 on bottom. That's still not reduced, but it's closer because I don't have fractions and decimals mixed up. What would I need to reduce it by then? Yeah, if I divide by 5, I would actually get 4 on top, 5 on bottom. It's 4 pi over 5. So my omega is 4 pi over 5. Another option, just since I'm gonna mention it since we're here, you could just multiply the bottom by 2, because 2.5 times 2 is what? 5. So if you happen to notice that, as a general statement, not just every decimal is going to do that. So 10 is a good choice. But on this one, 2 would have worked as well. So anyway, we've got an omega is 4 pi over 5. So our equation for our object is d equals, and then we have negative 5 for a, sine, our omega is 4 pi over 5, and then t. Yes, ma'am.
On exams and quizzes,
Yeah.
would you like us to do every step of that, or can we just show, like if we were to just type that in the calculator instead of changing the decimal and all of that? Is that okay?
So that would be fine. Right. No, that would be okay. I want the answer to have the 4 pi over 5. So I don't want it to lose the pi part of it. Okay. But you could definitely go from the 2 over 2.5 and let your calculator turn that back into a nicer fraction. That's okay. This class is not supposed to teach you how to do fractions, so if you want to use your calculator for it, I'm cool with that. Okay, I have one more question. Are you ready? One more example. It's related to these. This is simple harmonic motion. Okay, so a different version of a question would look like this of these. So an object moves in a simple harmonic motion. This time they actually give us the equation. The other two we found equations, right? And it asks us to find A, the maximum displacement, B, the frequency, and C, the time required for one cycle. So it's asking us to find 3 pieces of information, 2 of which we've talked about and 1 of which we've not. So let's start with A. That's the easy one. We've talked about that one. What is the maximum displacement? Right. So the maximum displacement is actually the absolute value of A, right? The amplitude, which is a positive on this one, it's 10. Okay, so that's the most direct one. We've talked about that one. We just haven't had that new terminology until this section, but it's okay. B is a little different. We actually haven't talked about B. B asks us to find the frequency. That's not a word we've looked at, okay? The frequency is how quickly it repeats itself, right? It's kind of like period, all right? So frequency is actually found with the formula F equals omega over 2 pi. Now that should look familiar. What does it look like? It looks like period, but the reciprocal, right? It's the upside down of the period. So the frequency is the reciprocal of period. So you might jot that down as a reminder. The frequency is the reciprocal of period. So if period is 2 pi over omega, which it is, then frequency is omega over 2 pi. Well, what is the omega in this problem? It's 4 pi. So 4 pi is on top, 2 pi is on bottom, right? So what's 4 pi over 2 pi? Just 2. This would be 2 cycles per second. or per whatever unit that it was working with. I'm going to go with seconds for this one. They'll give you some units. I don't have any units on this actual problem, which is a little bit of my fault in terms of a flaw in the problem, but the same idea is there. Okay, so it's 2 cycles per second. So the third question is, what is the time that is required for 1 cycle then? If you can take and get 2 cycles in 1 second, how long is it going to take you to get 1 cycle? Yeah, 1/2 of a second.